A very warm welcome in the class of Mathematics 1. Today our topic is sequence. Myself Rupak Bhattacharjee, Assistant Professor, Department of Mathematics, JIS College of Engineering. Now, in this particular topic, or I should say that in this particular lecture, when we are going to introduce what is sequence, in mathematical point of view, there are some prerequisites. So those prerequisites are, first of all, the idea of numbers or the number line. So this is very much important for us because you will feel that after some time that we are going to link our idea with the number line. Next, our requirement is also there in the concept of mapping. And finally, we also need the concept of limit and the standard limit results, which we have learned before continuity differentiability part. So along with this, we are actually going to start the topic of today's class. First of all, we are going to learn this like a story. That means you can relate this particular description whatever the basic idea you have related to mathematics. It is not at all mandatory that you need to know a hardcore mathematics for initially identifying and realizing this particular thing. Here we are stating that a sequence is a list of numbers. That is why we have written it in the prerequisite that we need number line. And what are the numbers? We are denoting it by A1, A2, A3. This is importantly dot dot dot, then AN, and then again it is dot dot and dot. Means you are not in this particular representation, you are not restricting yourself up to a finite number of numbers. Now you can get one sequence, one specific sequence where your A1 can have a value. Similarly, another one can have another specific sequence where the value of A1 or the number what we are going to write in the position of A1 may be different. So we are actually writing it in an order where each of A1, A2, A3 and so on represents a number. So these are nothing but the representations or the notations of the elements of this sequence. These are the terms. You can see that it is emphasized. We are calling these as the term of the sequence. Now, if we think for a specific sequence like 2, 4, 6, 8, 10, 12, and it goes to 2n and so on. Here, this is my first term, 2. So I will denote it A1 is equal to 2 in this specific sequence. Similarly, our second term is 4 and third term is 6 and so on. We will get our nth term which is 2n and which is denoted by an is equal to 2n. Now the integer n, that means this suffix position, actually it is called index in this context of sequence, and it is index of an and it indicates where an occurs in the list. Means if you see A3, you can get a conclusion that it is in the third position of the sequence. If it is, obviously represented in the standard form A1 and so on. If someone's initial point is something different, then it may differ. And obviously for this particular specific sequence, what we are getting, that 2 4 6 8, it is not same as the sequence 4 2 6 8, because here you see the order and here you see the order. The order in this one and the order in this one are not same, so obviously they are not same sequence. Now proceeding further for this particular discussion, it is another way of thinking the sequence. We are getting A1, A2, A3 and so on, and we can say that if we write 1, 2, 3, 4 and so on, and if we through it by some function, and this function sends 1 to A1, this function sends 2 to A2, sends 3 to A3 and so on, then more precisely we can say that an infinite sequence of numbers is a function whose domain is the set of positive integers. We know that it is our domain and this is our range. If we have a given function, then obviously from this we can say that it is going to be the domain of this particular function as the positive integers. Now what we can see, that our sequence can be described by writing rules that specify their terms. What they are specifying? Now such as we can take an is equal to root over n. Now you can check it here. For this one we can write it as root over 1, then root over 2, because we are taking the value of n starting from 1 and so on. So we are getting it as this particular sequence in by listing the terms. This is another representation. Similarly, if we take this particular sequence, then we can get this one, because any one of us can put the value of n starting from 1 and we can get this 1 by 1 is 1 and minus 1 whole to the power 1 plus 1, that is 2, that is minus 1 whole square, and we get 1. In a similar manner, if we proceed according to the value of n incremented by 1, we will get the second term as minus 1 by 2, then 1 by 3 and so on. Similarly, for the series, for the sequence Cn is equal to n minus 1 by n, we will get this one, and you can just check this one, but this is very interesting because what I want to say, that if you put the value of n starting from 1 2 3 and so on, and if you go on, you will see that the value or the functional value, what you can say, that what we are getting, it is coming as 1 and then minus 1 and then 1 and then minus 1 and so on. So it is a very important observation from what we can make, that what is the pattern it is actually following. We will come into this particular discussion after some. Now there is a very beautiful pictorial representation of these three sequences. Look at the first one. If n is equal to root over n, and if we put the value of n equal to 1, 2, 3 and so on, in this number line you will get, if you put n equal to 1, a1 will be 1, then a2, a3, a4, a4 will be 2, so a2 and a3 will be obviously within a1 and a2 and so on. And if you want to represent this in our xy plane format, so here it will be in an plane. As n increases obviously by integers 1, 2, 3, 4, 5 and so on, so it is a discrete plot, and you will get an as 0, 1, 2, 3. It is our axis and the values are a1 is 1. You can see that a4, that means you can just map it and you will get that it is going to be 2, what you get here, and these are the intermediate values. After that, when you are coming to n equal to 1 by n, you can have another observation that as it is going on and on, the values are coming in this direction, and maybe it will go to some fixed value. We will check it. And for this one, where an is equal to minus 1 whole to the power n plus 1 into 1 by n, you can see that for this minus 1 whole to the power n plus 1, this component, your values will come from positive to negative, then positive, then negative, then positive, and so on. That means it is changing its characteristics from positive, negative value. Now, the last discussion with the graphs or with the pictorial representation, it will actually generates the idea what we are going to share here now, the idea of convergence and divergence. So all of you know the concept of convergence and the concept of divergence, that if we are getting this particular thing and if it is coming into a particular point after a certain distance, then it is called as converging rays. And when we are getting these types of situations, when these are going far and far, if you go from this direction, that means if you are going far from this plane, you will see that their distances of these rays will also increase, and this is called actually convergence situation, and this is actually called divergence situation. You know this. Now we will check that how we are going to relate this with our discussion. First of all, if we take this particular sequence where the sequence is going from 1, then 1 by 2, 1 by 3, 1 by 4 and so on, obviously all of you are able to identify that it is nothing but the sequence 1 by n. So as this index n is increasing, you will see that n is approaching to a single value or to a particular value. Like this particular example, you will see that as it is going on and on, immediately the values are growing smaller and smaller, and this particular being smaller actually going towards a number 0. All of you are able to understand that 1 by n, n tends to infinity, will be going to be 0. So it is clearly written whose terms approaches 0 as n gets large. But in this sequence, in the next one, what you see that 0, 1 by 2, 2 by 3, 3 by 4, 4 by 5 and so on. Whose terms, these terms are actually approaching to 1, because if you again use this particular concept in this 1 by n, you will get 1. Similarly, if we take the sequence like this one, you will see that the resulting outcome is growing bigger and bigger and bigger. So as you go from 1, 2, 3, 4, 5, 6 and so on, you will get the outcome of this particular function, which you can treat as a sequence that is growing bigger. So as it is growing bigger, it is not possible for this particular sequence to converge for a particular single value. And finally, we will get this particular sequence, which is already discussed in the last slide. Is when they are actually saying sometimes 1, sometimes minus 1, sometimes 1, sometimes minus 1, and it is coming in a pattern. It is coming in an regular interval. Then this is also not converging, but this is also not going far and far. So this total story is actually giving us a limiting value if it converges. And we are going to discuss, or rather we are going to summarize this one with the formal definition of convergence and divergence. But before that, just I want to make it clear to our viewers that what is actually happening under the curtain of convergence and divergence of a sequence. So now we are entering into the formal definition, and this formal definition tells us that the sequence an converges to the number n if for every positive number epsilon you have to choose it, there corresponds an integer capital N such that for all n like this, means you have chosen one n, and for all n like this means all n, all small n are selected from this region which is greater than capital N. You will see that mod of an minus L is less than epsilon. So if this happens, then that sequence is called convergent sequence. And if no such number L exists, obviously it will be a diverging one, and then we say that an diverges. Now we can also understand this one. There are some representation techniques, but we are going to understand this one from one small pictorial representation. Now what you see, it is A1, you can see it, then they are A2, A3, and so on, they are going on. But after an, that means when the value of small n is capital N, after that we are getting all values of an, where n means small n is greater than capital N. All values are bounded within an interval L minus epsilon, L plus epsilon, which is actually written here like mod of an minus L is less than epsilon. If you break it, you will get this, that L is, all the values are actually within L minus epsilon and L plus epsilon. And if it happens, then we can say the sequence is convergent. But in some cases, you can see that it is not happening, and in that case, you have to say that it actually diverges. Now, we are going to give you some examples, and very basic examples, that what will be the limit of 1 by n when n tends to infinity. They are saying that it will be 0. We also know that it will be 0. But when the question of proving this particular claim, and obviously it will be from definition, then we have to think for the expressions what we should write in our record. So let epsilon greater than 0 be given. Now we must show that there exists an integer n such that for all n what is stated in the definition, n has to be greater than capital N. Then an, here an is 1 by n, minus L, here L is 0, we will less than epsilon. It has to satisfy. Now this implication will hold good if 1 by n is less than epsilon. If you break this modular sign, you will get it, or n is greater than 1 by epsilon, because you can just use it in the reverse direction. Now, A, capital N, which we are actually searching because after that all n's, all small n's will satisfy this one. Is any integer greater than 1 by epsilon? Because if you take 1 epsilon which is greater than 1 by epsilon, then this implication will hold for all n greater than capital N. And then this proves that limit n tends to infinity 1 by n is equal to 0 from definition, the definition what we have learned in the last slide. So I had a request to all of you that these are totally conceptual and it requires initially a lot of cool brain to understand and to represent it. But once it is realized by your brain, then you will be very much familiar with this particular proof technique. So I am not explicitly discussing the proof of the second example, rather example number B under 1, but you will see that the approach is same, only depending on the requirement we are changing the expression of epsilon. Clear? So now proceeding further, this is a very beautiful example taken from Thomas calculus, that we have to show that the sequence 1 minus 1 1 minus 1, that means where it is alternating, it is actually diverging. So what I want to say, it is clearly self-explanatory what is presented over here. I have taken this one from that particular book, and if you read it you will be very much comfortable to understand that one. My only one point to raise this example in this lecture is that we can give the same argument for any positive number epsilon smaller than 1, which is not necessarily has to be 1 by 2. Here we have taken it is 1 by 2, but we can take anything maintaining these conditions, and depending on that the convergence criterion will be achieved, or this particular zone will be created in different locations, but ultimately the zone will be created to prove that whether it is convergent or not. Now the same thing for another divergence, because the previous one is an alternating example, and here it is completely root over n and it is diverging because as n increases root over n also increases and the gap corresponding to consecutive two elements in the sequence actually increases. So it is very much obvious that it will be something like that. Now there are two pictures and we will discuss these two pictures in the next slide, but before that I want to say one thing. You please emphasize on this shaded part and you please emphasize on this small m and capital M. If these blue dots are nothing but the terms of any sequence, you can see that if we fix this m, and it is obviously a negative number because it is coming the lower part of this axis, and capital M which is a positive number, and if we are trying to restrict our sequence within these two and if it fails, then obviously it will be not a converging sequence, other we can say it is a diverging sequence. So how we are going to represent it, they look at this, the sequence an diverges to infinity, please recall the first picture, and similarly it will diverges to negative infinity, please recall the second picture for your own preference and facility. I am going to give you these two pictures one more time, and if we come to this, that it will be diverging to infinity for every number m, capital M, what you see in this particular graph, that there is an integer n such that for all n larger than capital N will be greater than n. An will be greater than n, means you are bounding something and it will go crossing and something like that. You are bounding something in the lower part, it will also cross. So obviously in that condition we can write that limit n tends to infinity an goes to infinity, and obviously it will be true for the negative infinity also. Now if we proceed further, we will get some basic theorems related to sequence, and those are, if we take two sequences an and bn, obviously of real numbers, and then if we get that an and bn both are converging sequences and they are converging to capital A and capital B, then there are 5 rules. Those are basic rules, but we can use it in our problems. That if we sum them up, the sequences, and then take the limit, it will give you the summation of the limits separately. Same thing is for subtraction. Same thing is for multiplication by a scalar quantity. Same thing is the product of them, and same thing obviously about their division, and we have to make sure that this will only exist if capital B is not equal to 0. So these rules are actually used for finding out the solution of the problems related to sequence, and the name of the rules are according to their activity: sum rule, inference rule, then constant multiple rule, then product and quotient rule. Okay, so if we go for this example number 3, then we can see that all these are actually coming from the theorem and corollaries what we have generated in the previous slides. So limit n tends to infinity minus 1 by n. This minus is nothing but a scalar quantity. So we can bring it out, and then we will get limit n tends to infinity 1 by n, and limit n tends to infinity 1 by n is 0. It is already known to us, so it is nothing but the example 1a, because we are using that scalar multiplication rule of this sequence. In the similar manner, for the second problem here, that is b, we can exhibit that it is going to give us the result with the help of the difference rule. For c, we can again use this, that it is a product of two sequences, both of them are obviously converging. And example number D, where sum rule and quotient rule both are applied, and we obviously get the result is also a finite number. Now a very important statement which is called the sandwich theorem for sequences. Sandwich means, all of us are very much familiar with this, that if we take this thing and this thing to bread, and if we give some particular material over there, if we press them up, we create a sandwich. This particular concept is used here, and we are taking this, that an is less than equal to bn is less than equal to cn, means bn is in the sandwich position. Now what we can conclude related to the characteristics, because here limit n tends to infinity an and limit n tends to infinity cn, not the bn, is given, that is equal to l. From this we can conclude that limit n tends to infinity bn will be also l. Look at this, if cn is coming to l, and if an is also coming to l, and if bn is also always in the sandwich position, that means bounded by an and cn, so as n increases, an and cn are actually going to a fixed number, same number, and as bn can't go outside from an and cn, bn will also reach to that particular number. So this is pictorially very much clear to all of us that what is the meaning of sandwich theorem. Now we can take another example where 1 by n tends to 0. You all know this. So if we have to make cos n by n, we can write it as cos n by n is within minus 1 by n and plus 1 by n, and minus 1 by n is also going to 0. Plus 1 by n is also going to 0. So cos n by n obviously equal to 0. And using the sandwich theorem, actually we are claiming this result. Similarly, for B and C, these two are for you, and you can check it that whether and how we are able to make it using sandwich theorem. Now, there are very important 6 standard limits which we need for solving the problems of sequence. Just one thing I want to mention, that is what is also mentioned over here, that in the formulas 3 through 6, x remains fixed as n tends to infinity. So n is varying over here, x is fixed. In some cases x will follow the criteria where it is given that x is greater than 0 or mod x is less than 1, it will follow, but it will not change the result of the limit. And in some cases you can take any value of x, in the case of 5 and in the case of 6, but ultimately, except the result of 5, you can see that all the results are not depending on x, only the result of 5 is depending on e to the power x. So now finally we are reaching into the almost the last part of our sequence discussion, basic discussion of our sequences. We'll get another idea called non-decreasing or non-increasing. Non-decreasing means it will not decrease. It may increase or may same. Similarly, for non-increasing, what we can claim that it will be same or it will go to decrement, but it will never increase because it is crystal clearly mentioned that it is non-increasing. And if an is less than equal to an plus 1, it is the notation of this particular statement for non-decreasing. Now, if we get a sequence is non-decreasing or non-increasing, then the sequence an is called monotonic in nature if it is either non-decreasing or non-increasing. Monotonic means it will maintain the characteristics throughout. It is actually monotonous, means you are not going to get the variation from this point of view, whether sometimes it is going bigger, sometimes it coming down, and so on. That means there is no zigzag and there is no such ups and downs. It will be in a single straightforward characteristics. Now, why we are discussing this concept of monotonic particularly here? Because the reason is we also have one very important result or the theorem, the monotonic sequence theorem. It tells us if a sequence an is both, is very important, both bounded and monotonic, then the sequence converges. You don't need to check other things. Means it is bounded means it will never cross. You can go along and along and along and along, no problem, but it will never cross this boundary. Then it is called bounded. And if it is monotonic also along with this boundedness, then obviously the sequence will converge. And look at this, if it is monotonic nature is not mentioned, then we can say something like that, because it is not monotonous, but it is monotonous as well as bounded. So we have to think for these types of presentations, and it will converge because it will, though our cap n is increasing, an is approaching to a fixed value in that particular axis. Okay, so this is the concept of monotonic sequence theorem, which we need this idea to prove some problems related to this. So what we get the completion of the sequence, we have made this particular video lecture with the help of these references, And finally, these are some very basic MCQ assignments for you, but after that you have to do the solution of the sequence problems. So finally, I want to thank you all. Happy listening, happy learning.